Yes.
Okay, let's start. So a very good morning to all of you. I hope all of you are getting coffee and breakfast and all set to go. So let me start by a small story. Amazon EC2, the one we call Elastic Compute Cloud, went down on April 21st, 2011. Now, many people had no idea what Amazon EC2 was. And I suppose many of you even don't know what Amazon EC2 is in its real sense. But what people noticed was that their favorite website was not working. Quora, or Foursquare, if you know what Foursquare is, it's this little thing that you install in your phone. And then Reddit. All these websites were not working suddenly. That's what people noticed. And then none of these websites could get their services up and running until Amazon fixed the problem, which happened a day later. Now, this story tells us two things. One, cloud computing has already become a part of our technology landscape. It's invisible, but it has already become indispensable. The second one is porting your programs that are already in the cloud is a huge challenge. How come? Because only Amazon went down. There were many other clouds already up and running. They had no problems. Google had no problem. Rackspace had no problem. And still, these guys could not, move their stuff over from Amazon to the other one and get it up and running. Why? Because they couldn't. So still, this portability aspect of cloud programming is hard. So this is my thesis topic. An abstraction-driven methodology for application and data portability in cloud. So welcome to my talk. If you don't know me, I'm Ajith. In one sentence, this is what I'm doing.
Hey Ajith.
Yes.
Ajith.
Yes.
The board looks totally white for me. So can you or somebody email out all the slides?
Yes.
We can't see slides.
No, I don't think it would work. So
I can do Skype, iShare or Skype.
no need.
No, background is white.
Can you email the slides to Dr. Shet from my computer? Yeah, it's open. Yeah.
Oh, yeah.
So yeah, Dr. Shet, slides will come your way. So this is my thesis in one sentence. What I'm proposing is these carefully crafted abstractions. Abstraction for both development, management, and deployment of cloud applications. They help you to do that perform that in a platform agnostic manner. Now, you might not understand all this right now. My mission is to make you understand. Okay, let's move ahead. So, this is what we are going to look at today. I'm basically going to give you the motivation from this research and the significance, and then the research questions and what solutions that I propose in my research, and then basically what I have done so far, what's planned ahead. And of course, there will be time for questions and comments. If there are questions in the middle, I encourage you to ask questions, but if they are going to take time to answer, say more than 1 minute or 2 minutes, then we are going to answer the questions at the end, and Sanjay will be taking down whatever the questions, if they're important and if they need a specific follow-up. Okay. Before we start, cloud computing in a nutshell. Now cloud computing is somewhat of a polluted term. Why? Because so many people have thought of different things when they say cloud computing. For me, cloud computing is this as a service aspect. What do I mean by that? The first clouds that really came up were infrastructure as a service. So basically, Amazon, who provided these virtual networking and virtual computing facilities, was the cloud. And what they basically provided was virtual infrastructure as a service. And then there are these platform as a service guys. What's this platform? Platform is basically a placeholder for your application. You don't deal with virtual machines or networking or IPs or any lower level detail for that matter. All you think of is your application, and all the what's provided to you by the provider is this placeholder that you put your app and everything's good to go. Then software as a service. This is something that you will probably be using already. Google Docs, Office 360. This is software provided to you as a service, probably running on a platform cloud. Probably, and it may not be. There's some other things in the picture that's come recently. That's why I call it X as a service. So now there are guys that are providing data as a service. There are people who are providing analytics as a service. IBM is huge into analytics as a service. And then there are these nice things like Hadoop as a service. Hadoop is this distributed data processing framework, and anyone who's worked with Hadoop would know that setting up Hadoop, and that's a big pain. Amazon provides you Hadoop as a service. So you basically write your program, upload your data, press a few buttons, and voila, you are running on a Hadoop cloud. So all this taken together is what I call the cloud. So cloud is everything. What is my motivation for this research? Again, let me tell you a story. This time it's about Dr. A, the biologist. Now, this is a real story, but I have put imaginary names just to protect the privacy. I don't want to put real names. So Dr. A is a biologist, and this guy is a experimental biologist, meaning he does these experiments with a device called the NMR spectrometer. So NMR spectrometer, all you have to know is that it's a huge machine. NMR stands for nuclear magnetic resonance. It's a huge machine. You put these biological samples in, and then it spits out a big chunk of numbers. So the work of Dr. A consists of running this machine, getting the numbers, and then the numbers he plots them on a graph as a spectrum and looks at it and say, aha, there you go, this is this compound. And he can't do it just like that, so he has to run it through certain numerical processes, statistical algorithms to get it to a level so that he can interpret it. He uses his lab computer to do that. The catch here is that Dr. A works for the military, and he has some of his experiments are quite sensitive. So he needs to be really, really careful of what kind of data that he puts out, how would he keep the data and so on. The problem he has is that he uses an old MATLAB program that one of his old students wrote. This program is somewhat unpredictable in the processing time. Maybe it takes a few days for him to process it. This is a big no-no, because if he figures out that he injected a wrong parameter, or he didn't set some parameter correctly, then the problem is that he'll have to wait a few more days to run the experiment, get the results, and do it again. Dr. B, who is the head of the computer science department, said to Dr. A once, you should try to use the cloud once, because if you moved your stuff to the cloud, you could probably do your number crunching much more faster. And you know what? We have collaboration with Microsoft, so we could use the Windows Azure cloud as much as we want. The problem here is that Dr. A, first, he doesn't have the budget or the money to hire programmers and expertise that is required to move the program. Two, he's not savvy enough to write it himself. Three, he is worried about the sensitivity of the data. Not all experiments can be processed in the cloud. He could do some of them, but not all of them. So this is the highlight of the story. There are many domains that want to use the cloud. There are many applications that you could potentially put in the cloud. But there's significant expertise that is required. And then not everything may go into the cloud. Not because of technical reasons, maybe for legal reasons. So you have to have the flexibility to deploy your computation into a platform of your choice. Now, imagine this. What if Dr. A could compose his programs using his own terms? So being a scientist, he knows exactly what sum normalization means. He would write you the equation saying, okay, if you have x, y, and z, sum normalization is the sum and then divide it by sum, something like that. But you ask him, go write that in Java or go write that in MATLAB, he is helpless, right? So what if he could write his programs using his own terms, using his own domain vocabulary? And then what if he could deploy these programs into a computing platform of his choice? See, I said computing platform. This computing platform could be the cloud. It could be a local cluster, like the cluster we have here in Kno.e.sis, or it could be your own desktop. Depending on the situation, depending on the data size, depending on the legal requirement, he should have the flexibility to deploy his computation to a cloud of his computing platform of his choice. Now, this is my motivation. The goal of my research is to make these programs portable so that you could put it in any platform you want and pretty easily composable. So in other words, develop, deploy, manage cloud applications in a platform agnostic way. Now, why is this significant? What is the significance? In terms of practice, there are two items that come into mind. One, there's a huge impact on cloud adoption. Why? Because now we are enabling domain scientists to make use of the cloud. So they don't have to learn new things. There's very small learning curve. Then the impact on cost benefits. Why? Because now programming for the cloud is not an expensive affair. You could do it much easily and with less cost. And of course, porting your programs, putting your program in Amazon versus Google is again not an expensive affair. So there's cost benefits on this one. So both of these are practical significances. What's important theoretically for an academician? For an academician, what's important is to understand the limits. What domains can you apply here? Or what are the limits of your abstractions that come into this field? What kind of trade-offs would you be making on migrations? Things like that are the theoretical significance. Understanding these will let you apply this proposed solutions in an appropriate way. So you can't do it everywhere. There are certain things that you can do. There are certain things that you can't do. If you use a certain level of, say, expressivity, then perhaps you can't migrate it properly, or it limits your migration, things like that. Okay, before we move on, a very short background. So I'm going to go through very quickly on this one, but if you, and hopefully if you have questions, we can ask later. But some of these terms I'm going to mention so that because I'm using them later in the slides. Okay, I've been talking about this abstraction level. What is an abstraction? An abstraction level presented as part of the part of the software language is basically the amount of detail required either to represent or to execute a certain concept in terms of a perceived zero line. What do I mean by perceived zero line? Let me show you. The absolute zero line in this context is hardware. What it means is if you write a software, it has to run on some hardware at the end. That's the point, right? So that's the zero line, the absolute zero line. There are these other things that will come into play. Say like when you go on writing your software, there are some sometimes you come across memory location and instruction if you write in assembly. That's concepts that are pretty close to the hardware. And then there are much higher abstract concepts like say methods, or objects, classes, and even design patterns. So if you think of design patterns versus memory location, design patterns are at a much higher level of abstraction. Why? Because you need a lot of detail added to the design pattern for it to run on a hardware. So the level of abstraction increases on this direction. Now, the perceived zero line is somewhere here. Depending on what you do, you place a zero line somewhere in the middle. So when you think of abstractions, you think of how am I going to represent it. Say let's say we put it here. Let's say we put it at the object level. So when you think of something, you are thinking, how am I going to represent this in terms of objects and classes, not in terms of hardware. You are only thinking of, okay, how am I going to represent this design pattern with objects. So that's what I mean by perceived zero line. How do you measure this, level of detail? So one concrete thing you can measure is the lines of code. How many lines of code do you need to, expand this so that it represents the concept that you it represents your concepts that are on your zero line. Okay, so now I hope you got the picture of what do I mean by an abstraction. Domain-specific languages, one of my favorite terms. So a domain-specific language is a specification language that has abstractions on a particular domain. It's trying to solve a problem in a particular domain. What do I mean by domain? Now, domain is what we call the domain of discourse, or sometimes it's called the universe, or universe of discourse. It is basically a set of entities that we take, that we look at in a certain perspective. We don't look at all the features of the entities, we look at some features of the entities, and maybe we put some formalization on top of it. So, this is probably somewhat Greek. Let me give you an example. Here's a nice example that I found on the web sequence diagrams. Now our domain is sequence diagrams. Hopefully you remember your software engineering 101, and sequence diagrams is this diagrammatic representation of doing things in a sequence. So you say A called B with this particular message, then B did something, B called C after that, and so on. Sequence diagrams is a way of representing that. Now when it comes to treating sequence diagrams as a domain, what are the entities that you are interested in? Only three: objects, messages, and actions. That's all you care about if you treat sequence diagrams as a domain. Now if you actually go to this website, you will see this nice little web interface. This is basically the domain and its DSL. What you see here, what you see here is the DSL, and what you see here is the graphical representation of that DSL. These two are equivalent, and in this domain you can only draw sequence diagrams. So our interest is only in sequence diagrams. Our language is tailored to represent these sequence diagrams, and that's all we do. That's all we can. How it actually draws these things, we don't even care. Our interest is in this domain, and it's obvious to you that if you want to write a web server or a web application, this is no language that it can't do that. It's not meant for that purpose. It's meant for only sequence diagrams. So this is the idea of a domain and a domain-specific language. A model. Models are abstractions. So in our context, in the software context, models are abstraction of systems, and or its environment, or all that it cares of. This is what we call the modeling hierarchy. Now, the people who do this, model-centric computing, they have this notion of a domain model that we are going to come to that. So, domain model is an abstraction of domain, if you think of a model as an abstraction. And the domain abstractions describe a computer-based system. There's another one called the meta model that describes the model. So you could think of it as a schema of the model. And similarly, there's a meta model on top of it that describes the meta model. So you could think of unending hierarchy here, but in software engineering you probably stop at around meta models. Why this modeling is important is that there are some tools that let you deal with meta models. So you could do meta models and you could say, okay, this domain should adhere to this meta model, and so on. And then there are other tools that let you deal with meta models and so on. But what is important for us in at least our research is we are around here. But I'm just giving you a reference saying that okay, there is a certain concept of meta models that come into play. Middleware. Middleware is again something that you probably heard so often here, at least from the Services Research Lab. So middleware is basically a software layer. Now, what is important about this software layer is that it's meant to provide you with some abstractions of lower level services through a very standard API or well-defined API, and the purpose of these abstractions is to provide a uniform interface for applications. Now, if you look at Phil Bernstein's paper that I've cited here, he's the guy who sort of coined this term, and in 1996 he wrote this nice paper about middleware to ACM, and this is actually a picture from his paper describing what the function of middleware is. Basically, the function of middleware is to provide this one API to a number of applications covering up different lower level services. What kind of lower level services are we talking about here? It could be operating system services. It could be web services. So it could be services of different granularity we are talking about. But the point is that a layer of middleware provides you a single API for the applications or for anything else, so that you don't see the heterogeneity at the lower level. Okay, now we move on to general research questions. If you guys want to take a break, 2-minute break if you want. Should we move on? Okay, good. So nobody's tired. The research questions, the general research questions I'm interested in is what kind of aspects should we model in a cloud application? What do we call a cloud application, really? What kind of things are there should we think of when we do a cloud application? If you are using abstractions for development, how should we use it? What is the way of utilizing abstractions in the development process? What is the way of utilizing abstractions when you try to interact with the cloud? So we call them cloud services. So here are some of my proposed solutions. So one of the things that we did the earliest was to model a cloud application. What kind of things should be modeled in a cloud application? So
do you have a list of all the aspects that you're considering?
What's that?
Do you have a list of aspects?
On a cloud application?
Yeah, you said what are the aspects that should be modeled? So
that is what I'm explaining right now. Yeah. Yeah, it's slide number 37.
Okay.
Yeah. So this is exactly the question that we are trying to answer right now. So we figured out that there are 4 things. You could call them aspects, you could call them semantics, right? So we figured out that there are 4 interesting pieces that you need to discuss or describe when it comes to a cloud application. One is data. The next one is the function. Then there are these non-functional aspects. So non-functional aspects I'll be explaining to you with an example, but non-functional aspects are things that you layer on the functionality, but they may not affect the function itself, but maybe other things. And then, very importantly, there are system semantics or system aspects. What do I mean by why did we did this separation? Let me take an example application and show you. Let's take a numerical data processing example, the one that we talked about on Dr. A. So if you are trying to build this application, obviously you will have to have the algorithms implemented in some logic, right? And of course there should be some data storage, data structures attached to it. That's obvious. So when you deploy this in the cloud, there is a system configuration that you are worried about. It may be a extensive, very explicit system configuration if it's an infrastructure cloud. It may be somewhat implicit or not very detailed when it comes to a platform cloud. But there's some sort of configuration that you have to do in terms of the platform. Then how are you going to interact with this? Let's say you have a service interface. Let's say, for example, you have a REST API and a SOAP API on top of your application, so that you could do a service call and pass your data and it pumps back the result. The data semantics or the data aspects are here. So data structures, data storage is what we say data semantics. Functional aspects is here. System aspects is obviously here. Where are the non-functional aspects? They are here, up there in the service interface. Why is this important? Because now you see you could change change these independently of each other. Let's take the non-functional semantics. Let's say you want to secure your interface, so you put HTTPS interface on top of it. That's not going to affect any of this. It should not affect your functionality, the logic that you are implementing, your data, or your system configuration. Or on the other hand, you would like to make this much more scalable. So you change your system configuration, but your functionality or data does not have to change. Right? So like that, these aspects are mostly independent of each other, or we call them orthogonal to each other.
Okay, I have a question here.
Sure.
So it's clear that the setup, configuration, and service and all these things do come in when you consider cloud. But how does cloud differ from, let's say, sequential programming in the context of functional and data, which is what you should actually try to emphasize and make precise? Mm-hmm. Because that's where you can claim some contribution. That is, having cloud as the backbone allows us to exploit, like for example, data parallelism or some of the properties.
Right. So when we tried breaking this up in this way, so what we were trying to do was to figure out which pieces to focus on. So when you say cloud application, so there's a whole lot of things that come into play, right? So if you look at the functional aspects, yes, so we could drill down into the functional aspects and say, okay, the most important thing about cloud applications here is that these functional aspects can be there's parallelizing things and so on. So again, if you go to data, let's say, then data aspects are different in clouds than the others. So the idea of doing this high-level breakup is to figure out or to note which pieces to focus on. Now, if you actually go on through my presentation later, I'll highlight that. We are actually focusing on only two things. We are not considering the non-functional aspects or somewhat of the semantic aspects. We are only concerned about the functional and the data piece of it. So the idea of this sort of high-level breakup is to, carve out a piece, say, okay, we are focusing only on these two, something like that. And I should say that this breakup was inspired by the 4 types of semantics of a service that was done by Ajith and Ranabahu, these people, way back. So this was somewhat similar, but there were different things when you regard a service. But here, that's where the difference is primarily on system semantics, because for a service, there's no concern of the actual system that it's running on, because people perceive service as something that's external to them, so they don't care. But when it comes to the cloud,
Ajith,
yes.
it might be interesting to link KK's work with the system semantics.
Okay, right.
That proposal that was submitted to NSF, I think the aspects, for example, the cost model and other things,
Right.
that give you an abstract description of system semantics.
Right. Yeah, let's move on. So again, the core of this, the proposed research that I'm getting on to depends on a life cycle for application. Now, this life cycle is what we call a model-driven or a top-down process. So basically, I'm saying we should first do the data abstractions, design the data abstractions, then develop using domain abstractions or domain-specific languages, deploy and manage your artifacts using a layer of middleware. This is actually the core. This picture summarizes what I'm proposing. Right? This is the core life cycle of the cloud application that I'm proposing. Now you see that there's some of the details of, say, system semantics and these things are not coming into this picture. So basically, the domain abstractions that we talked about, or the abstractions of interest for your program, come there on the data and the functional part. And here, the abstractions of interaction come into play. Okay, developing applications. The key concept that I'm proposing in developing applications is use domain-specific languages. Why? Because now you specify your program using a very focused and abstracted language, and this allows us to generate a platform-specific application for the platform of choice. And these applications would be functionally equivalent. Now, what do I mean by this functionally equivalent? Obviously, if the platform is completely different, you can't do the same thing in all the platforms. But you could, at an abstract level, do a very similar thing. Now, here's an example, a practical example that we had to encounter. When you say you are undeploying an application, if it's an infrastructure cloud, what it means is that you'll probably, remove the application, shut down the virtual machine, and maybe even terminate it. Right? So there's no trace of this application whatsoever once you're done with it. But when it comes to a platform, what do you mean by removing the application? The platform gives you a little placeholder. So if you think of Google App Engine, the placeholder, the application placeholder that they give you are for life. Meaning you get one, it's there for you forever. So you can't forcefully, even forcefully remove it. What do you call undeploying? So basically what we did was we did an equivalent operation where you put an empty application. So there's an application already there, but it's empty. When you try to access it, it says there's no application. Right? So you see, it was functionally equivalent to undeploy, but they did completely different things. But at an abstract level, the operation was similar to removing the application. So that's what I mean by saying equivalence. Okay, let's look at how this whole DSL-based code generation works. There's our code generator, there are the clouds. What you do is you use a DSL to express your program, and then feed this to the code generation framework. The code generation framework creates these executable programs for the clouds 1 and 2. They are different, and they could be they're native programs that work on clouds 1 and 2. Say you come up with cloud N at some point, some later time. Basically what you do is you modify the code generator. The notice now is that this guy didn't change, none of these guys change. They don't have So as a user, you are only doing your program specification once. Now, okay, again, these programs, executable programs, are functionally equivalent. That's why I have covered them with a dotted line. Data abstractions. Data abstractions, in all the examples that I'm going to give you, data abstractions are integrated to to the DSL, but they are important because data abstractions play an additional role. This additional role is in migration. Why is this data migration important for us? Because data is mostly considered the most important asset, not even important than the code when it comes to applications. The code, yes, you could rewrite the code, and our framework lets you, regenerate the code just like that. But data, whatever you have collected already, is very difficult for you to move. But if you follow our abstract-driven programming model, you could very easily port your data as well. How? This is where the lifting and lowering concept on data migration comes in. Let me give you a really, really brief introduction to what's meant by lifting and lowering. It concerns three data models. Let's say model A and model B, and then there's a common representation. Now, we define two transformations. The one that goes from a concrete model to the common model is called a lifting transformation, and the one that comes down from the common model to another concrete model, we call it the lowering transformation. Now, you define these transformations on the data schema. At the instance level, you could use a data model A instance, pump it through the lifting transformation, get the common model, and go down to the other concrete model that you want. But this seems unnecessary. Why? Why is this, indirection? The indirection comes in handy when you have more than 3, let's say, data models. Let's say you have 3 data models, just to take an example. So you would probably need 6 transformations. Go from model A to B, B to A, then B to C, A to C, things like that. So there are roughly about 6 transformations. Let's say you add another data model. There's another data model that you have to cater for. In this model, you end up adding 6 more. So it's if you remember your graph theory, this is a fully connected graph, right? What's nice on using a common model is that you still start with 6 transformations, but you add a new one, you only need 2 more. You add another one, you only need 2 more. This one, if you add another one, I don't even have enough space to draw the arrows. So this is the advantage of doing this, common representation-based transformation, or lifting and lowering. How is this going to be useful for us? The point is that now since we start with data abstractions, we get to create our lifting and lowering transformations at design time. So our compilers generate these lifting and lowering transformations, right? And when it comes to the migration time, let's say you want to go from A to B, you dynamically arrange the correct transformations, and you could go from A to B or B to A, because at the time you actually generated your program, the compilers could generate the lifting and lowering transformations as well. The compiler knows how it adapted the common model to the platform specific one, so it could generate you the lifting and lowering transformations. So the research questions, or the more focused research questions in this area, is what kind of conditions are there on these transformations? Can you transform all DSLs? What is there any special features of DSLs that come into play when you try to transform these applications? What kind of special conditions are there on data modeling? when you try to transform these applications, or when you try to do migration. I'll quickly go through deploying and managing applications as well. Do you guys need a break? We could take a quick break if you want. Take a cup of coffee. No? Okay, good. Using a middleware, you could provide these abstractions to different operations, and there will be different behaviors at the lower level, but still at the higher level as a user you would only see the same behavior. Now here's what I mean by that. So if you think of this sort of middleware where you have a deployment and a management interface and cloud adapters in the bottom, this is exactly what we did in AutoCumulus way back. So there are these cloud adapters, and what you do is you feed your application artifacts here to the deployment interface and ask it to say, okay, here are my application stuff that's related to my application. Put it in Amazon Cloud. So the users typically don't interact here, they interact here. Why is this important? Why is this advantageous to us? Because let's say tomorrow there's a new cloud provider. What do? You add a new cloud adapter. So that is the advantage. The users don't even know. All they know is that there's a new option now saying, you could even deploy here. Aha, nice. But they don't have to know what exactly is the API, what's the difference. So this is the idea of having a middleware layer to interact with cloud. The research question that is important here, or the focus research question, is what is the lowest or the smallest common set of features that you could do behavioral abstraction like this? There could be features that you cannot abstract out. Like so there are some features in Amazon, like this feature of elastic IPs. So they have a feature that lets you apply a static IP address to your instance. That's pretty hard to do in a platform. So in some certain platform clouds, there's no idea of a virtual network. So it's pretty hard to see that you could abstract that out completely. Right? So there's a important question here: what kind of features are best abstracted out? So we could put all these things together. So that's the whole idea of developing and deploying and managing artifacts cloud application. If you put the code generator, Dr. Prasad has a question, I'll probably answer that soon. If you put the code generator along with the middleware, so now your middleware, the function of your middleware is much more enhanced. I don't know whether you could even call it middleware at this level. Now, if you integrate the code generator with the middleware, users will be interacting with the DSLs, which are their domains, the deployment and the management interfaces. There's no talk even of the cloud. The cloud all is beneath. So there's no consideration of, what if the APIs are different? It's not a problem. So users don't see it. Now this is what I was saying. Now the middleware is, the function and the role of the middleware is now different. So we might not even call it a middleware layer. But if you look at again the original picture from Phil Bernstein, so you could think of it as a standard API to access this. So in a sense it's really middleware, but in another sense middleware is not really the code generating type. And the question that Dr. Prasad had here was, is it one code generator or is it many code generators? It is many code generators, really, because it could be it's one code generator per DSL, but I should say it's most of the infrastructure on the code generator is shared. meaning at least part of it. So the parser is different, the code generation templates are different, but the actual process or the base process is almost the same. Okay, about the others that think the same way. I couldn't be the one who thought of this at the first, right? So there are people who think somewhat similar. Now, if you look at the cloud world, there are these new people that's come up in the last 2-3 years called cloud brokers. Their sole function is to give you somewhat of a uniform UI to access different clouds. Now, if you think of, say, things like people like RightScale, there's a service arm of Dell called Boomi, and there's GXS. GXS stands for General Service Integration, General Exchange Service. So there are these brokers and integrators that have a presence, and especially people like RightScale, they provide you this uniform interface to interact with different clouds. But their interactions and their integrations are primarily on a generic or at a development context. So if you go to RightScale and they have support for Rackspace and Amazon, I don't remember I don't know whether they have added new support recently, but they support only infrastructure cloud. So they have these concepts like start a VM. So start a VM, they'll do in Rackspace or Amazon or whatever the infrastructure cloud that they support. But you have to know what a VM is. It's not in a domain context. So it's in a very developer-oriented way. Similarly, if you think of DSL-based application generators, there's something called Romobile. Romobile is, I suppose, came up in 2007. In 2007, they were a really small company. What they did was they provided this nice little way of writing a piece of Ruby code, HTML and CSS, and converting that to a mobile phone application. So it doesn't matter whether you are trying to go for, say, iPhone, then Android or BlackBerry or whatever the mobile platform, they would let you generate one. And now they have this cloud piece as well. They have something called a hub. So you could, if you go through them, you could generate a little piece of application that acts as the backend for your mobile application. The other one, Mobile. Mobile is also a mobile application generator based on a DSL, and this is in a very academic context. So this was a project by a PhD student, Zef Hamel. I met him in Splash last year. So this seems to be the closest project that comes to some of the projects that I have. But again, their focus is on mobile devices, and their focus is not on the cloud. The mobile again, the mobile language is not domain specific. It's abstractions on events, if you think of it. Meaning, their perspective is that mobile applications are very event driven. So they have a nice abstraction for events. So you could, write a DSL in their language, a DSL script in their language that's basically a set of events, and that's the application. Now, the change that we have, why our research is unique here, is we focus on domain experts, not on developers. And our focus is very domain specific, and we focus on being an integrated solution. Meaning we try to develop and deploy and manage all three together. Why is this important? If you think of RightScale, let's say, RightScale doesn't care what application you put in. It lets you put any application. But the problem is when you try to migrate, they don't know whether the application that you have is very specific to Amazon or not, because they have no idea of the application. On the other hand, Mobile generates, say even mobile generates nice, domain independent. They let them write these applications domain independently, and then you could generate a very specific application. But there's no talk about how do you put it in the cloud, right? So we need a more integrated solution and specificity on the domain. Okay. Anybody need a break? Okay, good. Cloud middleware. What have we done in this area? This we developed a project called Alto-Cumulus. It's a layer of cloud middleware, and this was my internship project with Max at IBM in 2009. We managed to support 3 types of clouds: Amazon EC2, and of course Eucalyptus. If you know what Eucalyptus is, it's an Amazon clone. So they basically implement the same interface as the Amazon cloud. So we supported Eucalyptus too, and then Google App Engine, and there was a IBM cloud called the IBM HighPods cloud. The operations we tried to abstract out was primarily deployment and some management tasks like taking data backups, right? Undeployment, in deployment and undeployment, and then taking data backups and some sorts of small management activities. The point of this middleware was to make life easier for certain IBMers who would eventually market certain products in, say, they have this nice thing that they either install that in IBM internal cloud, or some customers may ask, put that on Amazon for us. So the process of putting that application was completely different. They wanted something, because they are doing semantically the same thing, but still they have vastly different APIs and different programs and all those things. And some of these applications are not one VM. They're like 10 or 15 VMs, like 2 for the database, 3 for the application server, things like that. So pretty complex. I'm very happy to say that Alto-Cumulus was a major influence in one of the new IBM products. So Max worked very hard with the product team to get it out. So basically the product called IBM Workload Deployer, some of the features in the Workload Deployer was influenced by the features of Alto-Cumulus. And of course we had pretty much wide publicity inside IBM on Alto-Cumulus. So this is this is my experience with cloud middleware, and we sort of proved it works in at least in a limited focused context. So in terms of DSL based application generation, one of the best examples that I can give you in in terms of the research that's come out of here is MobiCloud. So MobiCloud is this hybrid application generator. It lets you generate an application that partly runs on the cloud and partly runs on a mobile device. We support these EC2 and Google App Engine backends and Android and BlackBerry frontends for this one. This MobiCloud has its a nice UI that you could play around with. It's open to the public, and I'm very happy to say that we've had some awards as well. So we got the best demonstration award at CloudCom for this project, and then we were selected for a technical award at this Fukuoka Ruby Innovators competition. So it's been a pretty successful one, at least in terms of publicity. Now, what it does is that it gives you these abstractions in a specific domain, so that you could generate a certain set of cloud applications that have mobile front end. Here's a quick look at the DSL. So our whole idea is using DSL to generate applications. And I don't expect any of you to understand this. This is probably Greek to you, but what you have to notice here is that this whole script, which is probably about 9 or 10 lines, is one application. So when you actually run this through the code generator, this creates two UI pieces, a database, right? A controller that lets you talk to the database, right? Data structures for these things like, say, the task, right? So this little script encapsulates a whole big program. The other nice thing is that you don't even have to learn this language, because you could represent this visually. That's what our composer is all about. You could compose this by dragging and dropping little icons and connecting them, and without even knowing a single word of the DSL. But underneath, it's actually the DSL that does the work. Here's a quick look at a convincing that this is actually worthwhile doing. What you see here is these little numbers. You might not even see it. They are the lines of code for the DSL. These, the orange ones are for Android, the green ones are for BlackBerry, and this one, the bluish one, is for Google App Engine. So you see that there's a whole bunch of code that you have to write if you want to do the same thing with Google App Engine or say Android. The point is that it will be a human who's writing that code. So if you even consider even the part of writing the code, there's a lot of work involved. There's a hidden cost here. That is, if you think of, say, Google App Engine, there's a lot of configuration that you have to do. There's a certain configuration that you have to have inside your application. Things like those, we manage. And the most important piece is that here, if you look at the Salesforce one, basically it's one of those extensions that we did. So you could integrate a Salesforce backend to your application. When you do that, you see the code goes through the roof, because there's a lot of things that you have to do to integrate with Salesforce. Like Salesforce has this OAuth authentication. So managing OAuth itself takes a lot of code. And when I say code, I don't mean the library code. I mean the code that you have to write as a developer, right? So there's a big advantage when you go for these, extensions or a certain integration. The point that I'm trying to make is that there's definitely a significant reduction of effort if you use this, but only in this domain. So you can't, do a really generic app, but in this domain, if you consider the domain, you have a significant advantage. Scale. Scale actually stands for Scalable Cloud Application Generator. Now, it creates the purpose of it is, it's just like MobiCloud, but it's focused on a different domain. Its purpose is to generate these statistical workflows, just for people like Dr. A, who I mentioned earlier in my talk. So, the Scale right now supports Hadoop clusters. So you could deploy the Scale generated programs into a local Hadoop cluster or the one in Amazon. It supports Windows Azure using one of these experimental MapReduce runtimes called Daytona. It's by Microsoft Research. And it supports PC environments with a Ruby program. So if you have a Ruby interpreter installed in your computer, maybe Windows, Linux or Mac, if you have a Ruby interpreter, you could run the generated Ruby program. There is a very similar publicly available graphical composer. The DSL looks like this. Now this is not as Greek as the earlier one. Still maybe a little bit confusing, but now you see it's much more readable, and it has terms like sum normalize, load data, store data. Now the point here is a person like Dr. A that I talked about earlier would immediately know what sum normalization means. He knows exactly how it works. So a script like this could be composed by one of those. You don't have to know computer science to write a script like this. Of course, you have to understand a little bit about variables and function calls and so on. But that's very little compared to writing this in, say, Java, right? Here's the composer. It's exactly like MobiCloud, albeit the coloring and all that. Again, the operators you see here are different. Earlier you saw only model, we went to prod, and now there are many different operators. All you do is you just drag and drop them and connect them, and then the program gets generated. It will even tell you that if you make a mistake, it will tell you that you can't do this. This is not the right sequence and so on. Here is a very quick look at what kind of generated programs are there. Yes.
Okay, one question. So here, if we talk about other abstraction languages, for example, Peg or Peg. So in that case, do you compare that with performance when we are considering other abstraction languages?
I'm not very sure what you mean by
other abstraction languages.
Yeah.
Like Peg, maybe if I talk about on a cloud environment and I can talk about Hadoop. So in that case, we could talk about Peg or Hive.
So if you think of Pig Latin, Pig Latin is somewhere in between. Okay, something that I did not mention when I was talking about domains. Domains could be varying levels of granularity. So if you think of MATLAB, for example, MATLAB, some people call it domain-specific language. Why? Because MATLAB is basically for mathematicians. But mathematics or statistics, let's say, is a really, really wide domain, right? And if you think of Pig Latin is much narrower domain, but still it's much of a generic nature because it gives you flexibility on, it doesn't tell you what kind of data you are processing. Here, what we are doing is we are focusing on a really, really narrow domain. So we have restrictions on what kind of data we are processing and what kind of abstractions we are targeting. So our level of abstraction is much higher at this one. Pig Latin would come as one of the options here, I'd say. So Hadoop, you could even think of Hadoop as a certain abstraction, right? So our considerations are at a much higher level than say Pig Latin.
Right. Then the DSL will have to be created for different domains in a different way, right?
Yes.
Even the terminology.
Yeah, that's the idea. So what the basic idea I'm trying to push is that having a DSL in a very narrow domain context is much more useful than going for a really generic way of doing things.
Okay, you can think of Pig Latin as some language for manipulating tables, right? Essentially, it's like SQL.
Right. Yeah, exactly. So SQL, one could say it's a DSL, but it's a very DSL with a real large domain, right? We have real generic domain. We are considering a much narrower domain. So again, the idea here is that you could write 3 lines of code and it generates you a huge MapReduce program. What's not obvious here is that some of these statistical operations, let's say sum normalization, if you try to implement it in Ruby, it's basically a sequence operation. So basically you sum up all the numbers, divide each number by the sum, so that then the result is basically, when you add them up, it becomes 1, right there. So that's the idea of sum normalization. The point is, when you do a MapReduce program, either on Azure or on Hadoop, how do you do this? Because now you have to think of in terms of MapReduce. This guy, this graph does not show you the effort that's required in order for you to think of that, in order for you to manipulate your program so that it works on, you change of your algorithm so that it works on MapReduce. That burden is completely away from you. But this graph does not do justice to show that. A very quick publication coverage. I've taken slightly above 1 hour now. I hope hopefully it will be 5 minutes more and I'm done. So we've had several papers on alpha cumulus in 2009, mostly at Uppsala, and then in 2010 was when MobiCloud came out, and we have had 2 papers in CloudCom, which is probably the most successful conference for us. We had 5 papers there, and then we got invited to several others in 2010 and 2011. Scale was mostly done in 2011. So early 2011 we had a paper at a biological conference called BICOG, which in this paper we outlined the abstractions that we proposed for the particular domain and the actual DSL, and the application of it came in an article in IEEE Internet Computing. Related to all these, the cloud modeling aspect that I talked about, we talked about the modeling piece in a 2-part article in IEEE Internet Computing in 2010. So altogether there's about 11 publications covering pieces of these projects and these ideas. Okay. Research question coverage. Now this is sort of a precursor to what I'm planning to do. We've covered some of these things like what kind of modeling is there, or what kind of deployment, and what is the deployment strategy, and all these things we've covered to some extent. But what we haven't covered is these theoretical aspects of what are the features of languages, or what are the features of middleware, these things. So of course the features of middleware we talked about not in much detail in our earlier papers. They're sort of everywhere. So we have some partial coverage, but there's no one paper that you can point to and say, aha, that one has all the foundations. So based on this one, the work that I'm planning, that's sort of impending for me, is basically 2 publications. One is already work in progress for the journal. So I'm working with Dr. Ajith and Dr. Prasad on this somewhat of a theoretical paper that talks about features and limitations of language and data transformation for cloud computing, really. And the features and limitations on middleware, there's a planned publication. I'm not sure whether it's going to go for a journal or not. It's going to be mostly on the experience that we already have on the earlier project, as well as the experience we had on like the new projects like MobiCloud, because MobiCloud now has a small deployment support module, which is more like the middleware. So unfortunately, I don't have access to Abstractions anymore. It's IBM's property, right? So I have sort of a clone of Abstractions, which is not complete yet, but this paper is going to be part of that. The others that I want to do is I want to do a really detailed code analysis. We've done code analysis in the past, but there's room for improvement. So we haven't covered all the features of code or objective evaluations that you could do on the programs. And of course, there's a subjective evaluation, meaning based on human subjects. This one is half complete, but as with all other things, the human subject research is very, very tricky because you have to take permission, and there's a lot of legal things that are involved. So it's sort of still pending. The final thing that I want to do is to put all these projects out as open source, because I think MobiCloud has a real, especially MobiCloud, has a real advantage in being adopted in the community. And I'm being repeatedly asked, especially from the Ruby community, whether we are going to open source it. So there's a active discussion going on about the legal issues involved and things like that. So in summary, for me to finish, what I've said so far is that using DSLs to provide domain abstractions is actually a feasible way for you to develop cloud applications without considering a lack of deploy and manage applications in the cloud. So there you are. I hope I didn't go. Okay, I've gone 9 minutes over what I planned, but it's not 30 minutes, so hopefully it's not bad. not that bad.